Welcome everyone, I am Bishwashree Chakraborty along with my group members Harshita Gour, Uddipan Kashyap and Biki Kalita. We are presenting our topic on Logistic Regression, a study on classification using Logistic Regression. We are students of B.Tech second year from the Department of Computer Science and Engineering from Barak Engineering College. Today we are going to present our topic on Logistic Regression and how it is used for classification problem in machine learning. In this presentation, we will be covering the basic concept, working process, and real-world application of logistic regression in a simple and understandable way. So let us start with the introduction. Before learning about logistic regression, it is important to understand classification in machine learning. Classification is a supervised learning process where the model predicts a category or level based on the given data. For example, identifying whether an email is spam or not spam, detecting fraudulent transactions, or predicting diseases from symptoms. There are mainly three types of classification. First is binary classification, where there are only two outputs such as yes or no. Second is multi-class classification, where data is divided into more than two classes. And third is multi-level classification, where one input can belong to multiple categories at the same time. These classification techniques are widely used in many real-world applications like spam detection, fraud detection, disease prediction, and customer churn prediction. Now let us move on to the next slide. So, what is logistic regression? It is a machine learning algorithm mainly used for classification tasks. Even though the term regression is present in the name, it is actually a classification algorithm. The main purpose of logistic regression is to predict probability values between 0 and 1 using a function called the Sigmoid Function. Based on this probability value, the model decides the final output class. For example, if the probability is greater than 0.5, it may predict as class 1, otherwise class 0. Internally, logistic regression uses a linear equation and then converts the output into probability using the sigmoid function. That is why it is known as logistic regression. Now the question is, why do we not use linear regression for classification problem? The reason is very simple. Linear regression can generate output values below 0 or above 1 which are not suitable as probability values. It also does not provide a proper decision boundary for classification. Another issue is that it is sensitive to outliers. It means a single extreme value can affect the entire prediction line. On the other hand, logistic regression gives output values only between 0 and 1, making it more suitable for classification tasks. It also provides a clear decision threshold, usually taken as 0.5. So overall, logistic regression is considered more reliable and efficient for classification problem. Now, to explain the next important concept of logistic regression, I would like to hand over to my teammate.
Good morning everyone. Now I am going to explain the logistic regression sigmoid function, the mathematical model of logistic regression, the logistic regression cost function and gradient descent method, starting with the sigmoid activation function. So the sigmoid activation function is a primary aspect of logistic regression. Why? Firstly, let's understand about the sigmoid activation function. The sigmoid activation function is represented by sigma z equals to 1 by 1 plus e to the power minus z. Here in sigmoid function, the value lies between 0 and 1. And because of this property, it is very useful for logistic regression to use it for classification and for probability values. Of sigmoid function is in an S-shaped graph where the output indicates that the values lies between 0 and 1. When the value of z is greater than 0, the sigmoid output is always greater than 0.5. Similarly, when the value of z is less than 0, the sigmoid output becomes less than 0.5. So here the 0.5 indicates the decision boundary in logistic regression. As z approaches infinity, the output approaches to 1, and as z approaches negative infinity, the output approaches to 0. So overall, this means that this makes sigmoid an ideal function on converting any real value into a probability. Moving forward, now let's understand the mathematical model of logistic regression. There are three most important steps in mathematical model of logistic regression. Step 1 is compute linear combination. Step 2, apply sigmoid function. And step 3, apply threshold. In step 1, what we do is we calculate a linear combination of the input features. For example, in the presentation we can see z equals to beta naught plus beta 1 x1 plus beta 2 x2 dot 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 beta n xn. Here the beta naught is the bias term, while the beta 1 to beta n represents the weight associated with the different input features. Here this equation is known as the best fit line. Moving forward, instead of using the z directly, we apply sigmoid function in this, and applying sigmoid function we get a probability value between 0 and 1. If the probability value is greater than 0.5, we indicate that it belongs to class 1, and if it is less than 0.5, we indicate that it belongs to class 0. Here we are applying threshold to indicate that it belongs to class 1 or class 0, where 0.5 is the deciding factor or the decision boundary. Moving forward, now let's talk about the cost function. In logistic regression, when we consider the cost function, suppose we consider the mean square error cost function, where h0 xi is the prediction made by the model and y is the actual output. So however, in logistic regression, when h0 x, which contains the sigmoid function, is combined with the mean square error, the resulting cost curve becomes a non-convex function. Whereas in gradient descent method, the graph is usually a convex function. This is an issue because in non-convex curve there are multiple local minimas, and when we take out the slope of multiple local minimas, they are equal to 0, and which is why in gradient descent method it gets stuck at a point and it cannot move, increase or decrease in a non-convex curve because of these local minimas. So to fix that, we need another function which we apply in cost function to reduce this issue. The issue can be resolved by using a cost function known as log loss or cross entropy loss. In log loss, the cost function is defined as cost in bracket h0 x comma y equals to minus log h0 x if y equals to 1. On the other hand, cost h0 x comma y equals to minus log 1 minus h0 x if y equals to 1. Here we consider two equations. When we combine these two equations and put it in the mean square error cost function, we get a final logistic regression cost function with log loss that is shown in the presentation, and this cost function results in a graph that is convex, and gradient descent can finally find it effective and find the global minimum, which allows us to understand more about gradient descent. Now, what is gradient descent? Gradient descent is an optimization algorithm that is used to minimize the cost function and find the optimal value of theta. The updated rule is theta equals to theta minus partial differentiation of z with respect to partial differentiation of theta, where alpha is the learning rate. The learning rate controls the size of each step taken towards the minimum point. The process of gradient descent is firstly initialize the weight, calculate predictions using sigmoid function, compute the cost using log loss function, calculate the gradient, update the weight, repeat the process until convergence. So with every iteration, the algorithm moves closer to the global minimum and improves prediction accuracy. So in conclusion, we can understand the sigmoid function converts output into probabilities. The mathematical model combines linear equations and compute using the features that are provided by the logistic regression. The log loss function creates a convex optimization for gradient descent, and the gradient descent helps find the optimal parameters by minimizing the cost. Together, these components form the basics of the logistic regression function and make it one of the most important classification in the working of machine learning. Thank you.
So now let us discuss the different types of logistic regression. So moving forward, we have the first type of logistic regression, that is binary logistic regression. In this type, the output contains only two classes such as yes or no, spam or not spam, or pass or fail. It is one of the most commonly used forms of logistic regression in machine learning. The second type is multinomial logistic regression. This is used when there are more than two output classes. For example, classifying news into sports, politics, or technology categories, or recognizing handwritten digits from 0 to 9. The third type is ordinal logistic regression. This type is used when the categories have a meaningful order or ranking. For examples, ratings from 1 to 5 star or levels like low, high, medium, and depending on the type of output data, different forms of logistic regression are used in practical applications. Next, we have the decision boundary. Now, let us understand the concept of decision boundary. A decision boundary is basically a line or boundary that separates different classes in a classification problem. It helps the model decide which data belongs to which category. In logistic regression, the decision boundary is formed using the equation W transpose X plus B equals to 0. If the value is greater or equal to 0, the data is predicted as class 1, and if the value is lesser than 0, it is predicted as class 0. In simple words, the decision boundary acts like a dividing line between two classes. For two-dimensional data, it appears as a straight line, while for higher dimensions, it becomes a plane or hyperplane. Decision boundary plays a very important role in improving classification accuracy and separating data efficiently. So moving forward, we have the evaluation metrics. After building a logistic regression model, it is important to evaluate how well the model performs. For this, we use different evaluation metrics. One of the most important tools is the confusion matrix. It helps us compare the actual output with the predicted output. It consists of 4 terms: true positive, true negative, false positive, and false negative. Using these values, different performance metrics are calculated. Accuracy measures the overall correctness of the model. Precision tells how many predicted positive values are actually correct. Recall measures how effectively the model identifies all positive cases, and F1 score provides a balance between precision and recall. These metrics helps us to understand the strengths and the weakness of the model and improve its overall performance. With this, I'd like to conclude my presentation, and I'd like to hand over the rest of the presentation to my friend. Thank you.
Hey everyone, my name is Biki Kalita and I'll be presenting the final part of our topic, logistic regression. I'll briefly discuss its applications, advantages and limitations and conclude with the key takeaways. Now, let's look at some real-world applications of logistic regression. Logistic regression is widely used for classification problems where the output belongs to a specific category. In healthcare, it is used for disease prediction, such as predicting whether a patient has a disease or not. In email systems, it helps detect spam emails by classifying messages as spam or non-spam. Banks and financial institutions use it for loan scoring to determine whether a loan applicant is likely to repay or not. Businesses use it for customer churn prediction, which helps identify customers who may stop using a service. It is also used in sentiment analysis to classify reviews or comments as positive, negative, or neutral. While logistic regression has many useful applications, it also comes with certain advantages and limitations. Now, let's let's discuss the advantages and limitations of logistic regression. Some major advantages are that it is simple to understand and implement, computationally efficient, and provides probability based outputs that are easy to interpret. It works well for linearly separate data and is less prone to overfitting compared to some complex models. However, It also has certain limitations. It assumes a linear relationship between features and the log odds of outcomes. Its performance may decrease when dealing with highly complex or nonlinear data. It is also sensitive to feature engineering, meaning the quality of input features greatly affects the results. For very complex datasets, more advanced machine learning models may perform better. Now, let's summarize the key points of logistic regression. In conclusion, logistic regression is one of the most important and widely used classification algorithms in machine learning. It produces probabilistic outputs, making predictions easy to interpret. Because of its simplicity, efficiency, and effectiveness, it is commonly used in fields such as healthcare, finance, marketing, and fraud detection. It also serves as strong foundation for understanding more advanced machine learning algorithms. Despite some limitations, logistic regression remains a reliable and practical tool for many classification tasks. Thank you for your attention. This concludes our presentation on logistic regression. We hope this presentation has provided a clear understanding of the concepts and its applications. Thank you.